Hello, welcome to this next lecture in this series, the reactions of period 3 elements. And this is a pretty big one because there is quite a bit of chemistry to be studied in this, which is the reactions of period 3 chlorides. Okay, period 3 chlorides with water. All right. But before we go on to the reaction of the period 3 chlorides with water, let's just quickly see about what we know about the different chlorides. Yeah, what we know about the different chlorides and their structure and bonding. All right. So it's sodium, magnesium, aluminum, silicon, phosphorus 2, sulfur, silicon, phosphorus 2. All right. So let's say I've got sodium chloride, magnesium chloride, aluminum chloride, silicon tetrachloride. Phosphorus has got 3 chlorides, remember, PCl3 and PCl5. Okay, so these are the chlorides that are listed in your syllabus, so we will be sticking to those. We know that the bonding in this one is ionic, ionic, ionic. This is covalent. Unlike the oxide of silicon, the chloride of silicon is actually a simple covalent molecule. This is covalent, and this is covalent as well. All right. Structures. You know that this is a giant ionic lattice, giant ionic lattice, giant ionic lattice, simple molecule, and simple molecule. Right. The pH of the solutions formed. Let's just put it here and then we can use that to discuss. 7, pH actually around 6, but then your mark schemes and examiner's report suggest that they want something in the 6.5 to 6.9 range, so we'll stick to that. Okay, this one, a pH of around, say, 4, right? So pH of around 2, pH of around 2, pH of around 2, 0 to 2. Okay. Sorry. You can say 0 to 2. I will tell you why we are going with that range in a bit. Okay. Sorry, 0 to 2. Okay. So this is established that the oxides of the metals are, sorry, the chlorides of the metals are ionic. The chlorides of the non-metals are simple molecular, they're covalent. Okay. Now, one thing to remember is that here again, just like in the case of the oxides, as we go across the period, okay, as we go across the period, the bonds become less ionic and more covalent. Okay, and the reason for this is discussed based on the electronegativity difference between the two atoms decreasing. There we discussed with sodium with oxygen and magnesium with oxygen, aluminum with oxygen, etc. Here we can do the same discussion, sodium with chlorine, magnesium with chlorine, and aluminum with chlorine. So you find that as you go across the period, it becomes less ionic, more covalent. Now, sodium chloride can be thought of as perfect ionic. It's as ionic as they get. And you find that sodium chloride does not actually react with water, but it just merely dissolves in water. The lattice is broken, right, by the water molecules, and the ions get surrounded by water molecules. They get hydrated, we say. So you have sodium chloride dissolving in water to produce Na plus ions and Cl minus ions, because sodium chloride is perfectly ionic and the pH of this one is 7. Okay, it's a neutral solution. Magnesium chloride seems to follow that trend almost. Okay, a very simple reaction is, you can say magnesium chloride when dissolved in water produces the Mg plus 2 ions and two Cl minus ions. The ionic lattice is broken down by water, right? And the ions get hydrated. But if this were the same as that of the sodium chloride case, the pH of this one is supposed to be, should have been 7. But the pH is in the 6.5 to 6.9 range, showing that it is weakly acidic, and hence there is something extra that happens, something more that happens, okay? And that is because the magnesium ion, because it has got a +2 charge and it's very tiny, and the fact that, okay, the difference between the electronegativities of magnesium and chlorine is slightly lesser than that between sodium and chlorine, you find that this compound is not 100% ionic. It is mostly ionic, but there is a bit of covalent nature that comes into it. Let's say 80% ionic, 20% covalent. And that basically means the magnesium ion starts reacting with the water in this case. You will see a lot of these reactions, right? You will see a lot of these reactions in your A-level chemistry with transition metals, all right? You'll have 6 molecules of water that react with it to form what is called a complex ion, okay? Where the magnesium is going to form a complex ion. Sorry, these ones must be normal brackets, parentheses. Okay, +2. All right. Now, why is this ion written like this? That is because these water molecules use the lone pair on the oxygen to form dative bonds with the magnesium. Okay, the magnesium ion has got a greater covalency, so it ends up forming dative bonds with the magnesium. But this won't stay like this. Right, this won't stay like this. This will further ionize. This will further ionize to give Mg H2O5 OH, as in one of the water molecules ionizes to lose its H+, and that H+ ion comes out into the solution, causing acidity. And hence you find that the pH is slightly acidic. But why is it slightly acidic when it produces H+ ions? Because the position of the equilibrium is a little far towards the left-hand side, okay, which means only a little bit of the ionization occurs, and hence there's only a very low concentration of H+ ions in solution. Okay, this is the summary. All right. To summarize, if there is a discussion, I mean, usually you get away with this equation in your examinations. They don't expect you to explain everything. You just get away with this. But in case you are asked for a reason why the magnesium chloride solution is acidic, you can talk about this as the summary, where you say magnesium chloride reacts with 6 molecules of water to exist in a final equilibrium as Mg H2O5 times OH. This ion is going to be a +1 ion plus H+ plus 2 Cl- ions in solution. This is a summary of all the reactions, all the equations that we wrote just now. And this is the reason why magnesium is weakly acidic. Next, moving on to aluminium. Okay, you find that aluminium chloride is actually producing a much stronger acidic solution at pH around 4. Okay, pH around 4. And aluminium chloride is ionic, or that's what we know, that's what we think rather. But you know that the bonding in aluminium chloride is a little complicated. At a slightly higher temperature, it sublimes, it dimerizes to form Al2Cl6, which is covalent. Okay, showing that aluminium chloride, because the electronegativity difference is even less now, your aluminium chloride is even more covalent. Let's say aluminium chloride is, say, 65% ionic and say 35 or 40% covalent. Okay, so it's more ionic, it's more covalent and slightly less ionic than magnesium chloride. So the same thing happens. here as well. So you can write it simply as AlCl3, okay, aqueous, giving you Al plus 3 and 3 Cl minus ions if no, detail is asked. Okay, so pH around 4, or a more detailed summary would be that AlCl3, just like magnesium, reacts with water to produce Al, H2O5, OH. Remember, the Al is a plus 3 ion, water is neutral, the hydroxyl is -1. So this is this is +2 overall charge, plus H plus 3 Cl minus ions in solution. And if you're wondering why magnesium chloride gives a pH of 6.5 to 6.9, while aluminum chloride is 4, the reason is obvious. The position of this equilibrium is a little bit more towards the right compared to the position of the equilibrium in the magnesium chloride case. As a result, concentration of H plus is a little bit more. Okay, so those are the reasons for the magnesium chloride, aluminum chloride giving acidic solutions.